Welcome to the last part of our unit on polynomial functions. In this set of videos, we are going to be putting everything we've learned together to graph polynomial functions. Now, if you've ever graphed a cubic or quadratic function, you've already graphed polynomials. If you've graphed linear functions, straight lines, those are also polynomials. So our focus is mainly going to be on polynomials of higher order. So cubic, quartic, quintic, powers just keep getting bigger and bigger, and you can graph all of them. To graph them perfectly, we need to use calculus, which we don't have in a pre-calculus class. So we're not going to graph them perfectly. We're going to focus on a few different key features of the graphs: their end behavior, their x-intercepts, and the y-intercepts, and how these three things all come together will give us a fairly detailed graph of polynomials that is as best as we can get without making ridiculously large tables of test values or using calculus. You might feel a little intimidated about the prospect of graphing. We often feel that way about graphing as new learners. But as we learn a few key facts about the graphs of polynomial functions, you'll find that they are significantly more straightforward to graph than you might think. But it's worth to begin with a couple definitions and an idea of what polynomial functions look like when they are graphed. So we describe polynomial graphs as smooth curves. Now, the definition of smooth and what a curve is actually have pretty specific, precise definitions that you would learn in much higher level math classes. We're not going to use those definitions right now, but these words aren't arbitrary. But we can also understand them fairly simply. If you think of something that's a curve, obviously it curves, and notice it's smooth. There's no jagged corners. There's no edges. So polynomials don't have corners like this. Rather, polynomials are smooth and curving. And that's a really important thing to keep in mind when we're drawing our graphs by hand. They might not be perfect, but they should still be smooth. Let's do another polynomial. Let's say it looks something like this. Notice it has a lot of curves. Just like this one, we can separate this graph into two different parts. Well, this wouldn't actually be curving back in. It should really be curving outwards. That's a more appropriate graph now. But we can divide this graph into three parts: the beginning, the middle, and the end. Now, if we think of this as a piece of string, the ends of the string would be the beginning and the end. And so when we're talking about end behavior of a polynomial, we're only talking about the left side and the right side of the graph. We're not necessarily interested at the moment in the things happening in the middle. So we can do the same thing with this first graph that we drew. Get rid of the middle and just focus on the end behavior. Notice that to the left, this first one goes down, and to the right, it goes up. Now, if you're thinking of these as graphs on a coordinate plane, what are the four directions that we could go in? Left and right, up and down. And notice that we're describing the behavior on the left and the right, so the only options for each side is either up or down. And so one of the first things you want to know is, how do we figure this out? Where do we find the end behavior of graphs? And that comes from the leading term test. The leading term test. And so the leading term, as you may recall, is the term in a polynomial that has the highest exponent. Generally, we write that first, though sometimes a textbook will try to throw you off and like put x minus x squared. So we have to be careful just in case they aren't in that proper order that we were used to. And so it says if we assume f of x is a polynomial, so a to the power of n, and then we don't care about the rest of the terms, we're just interested in this leading term, a times x to the n. So n is the degree, and a is the coefficient of that leading term. And these two things tell us a number of different things. All that together are what we call the leading term test. Two of them are like, we already knew this, so we're not that helpful. Well, the third is really what gets to the end behavior. So the first one says that f of x, rather the graph of f of x, has at most n minus 1 turning points. Now you might be wondering, what is a turning point and why do I care? So this is probably the least valuable part of the leading term test for graphing polynomials. If we are looking at a graph and trying to write an equation for it, this becomes much more significant. But if we're giving the equation and going to the graph, then it doesn't necessarily help us as much. But at a turning point, let me erase this to make some space. If we draw a graph of a polynomial, we'll do a somewhat simple one. Everywhere it turns, everywhere it changes directions from going up to down or down to up, that is a turning point. So this polynomial that I've drawn has 4 turning points. So if we were to think, what kind of equation could it be? Pause the video and try to remember if it has at most n minus 1 turning points, what degree would this have to be? Now, because you can pause the video, I'm not going to stand here awkwardly for terribly long. I will assume you've come back. And so if 4 is equal to n minus 1, that means n must be 5 or bigger. So this is how it helps us analyze a graph to go to an equation. But our focus in this class will mainly be regarding going from equation to graph. So the second thing the leading term tells us is f of x has at most n x-intercepts. So for graphing a linear function, n is 1, we have 1 x-intercept. If we're graphing a quadratic function, we have n equals to 2. So pause the video and try to decide how many x-intercepts could a quadratic function have. I'll assume you're back after a short break. So how many can it have? If you said 0, 1, or 2, you'd be completely correct. If you only said 2, you'd be forgetting that we can draw a parabola that doesn't touch the x-axis, or we can draw a parabola that only touches it in one place. So we can get 0 and 1 number of x-intercepts in addition to 2 x-intercepts. But the piece de resistance of this formula, this theorem, this test, is that it tells us the end behavior of polynomials. And that's the first part of being able to graph a polynomial. So we need to think of how n and a interact. What types of things can they be? We know that the degree is always a positive whole number. So it can be 1, 2, 3, 4, 5, but it can't be -1, it can't be 1/2, not if it's a polynomial. And we know that a can be any real number. So it can be positive, it can be negative, it can be even or odd, any type of number. And so this degree, we ask ourselves, is it even or odd? That's how we can divide our exponents into 2 different classes. Even numbers that can be divided in half, odd numbers that can't be. A, we look at, is it positive or negative? We don't care if it's a fraction or a decimal. We don't care if it's even or odd. We just care if it's positive or negative. So I'm going to give ourselves a little bit more space because there are 4 different combinations. And this kind of makes sense because we can go down on the left, down on the right. We can go up on the left and up on the right. Or we can go down and then up, or up and then down. So we know that there's going to be 4 different combinations. So if you think back to probability and counting, if we have 2 options for one thing, 2 options for another, the product, a fundamental counting principle, tells us there are 4 different outcomes. And these are the 4 different outcomes. And we want to be able to describe, what do these things mean? How do we find them? So I'm going to erase this because we need this space. So we had both of them going down. We had both of them going up. We had one going down, one going up, then one going up and the other going down. Always describing it left and then right. So notice that these top 2, they're both going in the same direction. Same direction. And these 2 are going in the opposite direction. I just realized something. In order for this table to work out very nicely, I need to switch these 2 around. We'll see why in a moment. So if we think of these 2 things as the same, we might say they're equal or even. So when n is even, they both go in the same direction. Now, if we think opposite, starts with the same letter as the word odd. So if n is odd, it either starts high and ends low, or starts low and ends high. So that means the degree tells us whether the sides match or they're different. So if you think of things that get bigger, that are growing, you might think of something that's positive. So if A is positive, notice that the right side is always going to go up. And that's why I had to switch the other 2 around. So if it's positive and the right side goes up, what would have to change in order for the right side to go down? Well, it would need to be negative. And this gives us our 4 different combinations. Now, it's important also to note that just saying left down, right down, well, visually accurate isn't as precise as mathematicians like to be. So we tend to use something called limit notation that says if we're going to the left, x is approaching negative infinity. If you think of a coordinate plane, when you're moving to the left, you're approaching negative infinity. And so if we're going down, we would say x, when we're going down, we're describing the y values, is also approaching negative infinity. To make this saying we're going to the right, instead of approaching negative infinity, we'd be approaching positive infinity. And so we can use combinations of x approaching negative infinity to mean the left, x approaching positive infinity to mean the right, and then y approaching negative infinity to go down or positive infinity to go up as a mathematical way of expressing these directions. Now this video I feel has already become rather long, but before we go, I do want to do a couple examples of actually using our leading term test. So I've got a couple written out over here. So the first one is f of x equals negative 2x to the third minus 2x. Now for each of these, I strongly encourage you to pause the video, look at the leading term, and then determine, before I give the answer, what you believe the end behavior will be. That will help you check your understanding and make sure that it's actually making sense and you're learning it, so you can identify errors and places you might need to ask for help sooner rather than later. So here's your opportunity to pause. N is 3, A is negative 2. So N is an odd number. That means they're going to be opposite directions on either side. And negative 2 is a negative number, which means the right side is going to go down. So if the right side goes down, then the opposite would be the left side goes up. So we could say, I'm going to erase this to make space. X approaches negative infinity, that means left. So as x approaches negative infinity, y approaches positive infinity. And then as x approaches positive infinity, this is our right side, y approaches negative infinity, which is the arrow pointing down. Let's take care of another few, and we'll go especially quickly for these to keep the video time down. So g of x is 9x to the fourth. To save time, I'm just going to write the leading term. That's all we have to look for. Again, here's your opportunity to pause, kind of quiz yourself, and then hit play again to find out the answer. So A is positive, N is even. So even means the same direction, and A positive means the right side goes up. So I'm going to have up on the right side and up on the left side. Now I'll leave it to you to practice the limit notation. As long as you can identify these parts, you'll be pretty good for graphing the function, whether you have a mastery of that notation yet or not. Next, we'll do h of x, which begins, in fact, the whole function is just x, or negative x to the 6th power. Again, take a moment, pause the video, test yourself, and now that you're back, we can see that n is 6, which is even, so it's going to be the same on both sides. And then a is negative, which means the right side will go down. So down on the right, same on the left, you go down in both directions. For our very last example, let me see, k of x is 4 times x to the 5th power plus a bunch of other stuff we don't care about because it's the leading term test. Only that first part matters. So again, pause the video. And now that you're back, n is odd, a is positive. So odd means our two sides are going to go in opposite directions. A positive says the right side is going to go up. So the right side goes up, the opposite direction would be the left side goes down. So these are examples of how we can apply this leading term test to give us the end behavior of polynomial functions. Once we have this and two other things, one of which is the y-intercept, which I'm pretty confident you already know how to find, we'll be able to completely graph any polynomial function.